Dear students, in this video we are going to see the properties of inverse trigonometric functions. These properties are very important properties, and using these properties only we are going to solve the problems in the coming exercise. The important properties of trigonometric functions. The first property consisting of 6 results. First property, result 1, sin inverse of sin theta equal to theta. Sin inverse of sin theta equal to theta if theta belongs to the interval, closed interval, minus pi by 2 to pi by 2. That is, the domain of theta is minus pi by 2 to pi by 2. For that proof, let us consider sin theta as x. Sin theta as x. From this, theta equal to, operating sin inverse, you will get theta equal to sin inverse of x. So theta equal to sin inverse of, instead of x, you replace sin theta here. Theta equal to, if sin theta equal to x, then theta equal to sin inverse x, and that x is replaced by sin theta, so you will get sin inverse of sin theta is theta. That's all about this. So theta equal to sin inverse of sin theta. Similarly, second one, cos inverse of cos theta equal to theta. If theta belongs to the domain 0 to pi, closed interval 0 to pi. And also, similarly, tan inverse of tan theta equal to theta. If theta belongs to the domain open interval minus pi by 2 to pi by 2. Fourth one, cosecant inverse of cosecant theta. If theta belongs to the domain minus pi by 2 to pi by 2, except 0. Similarly, secant inverse of secant theta is theta. If theta belongs to the domain 0 to pi, closed interval 0 to pi, except pi by 2. And finally, cot inverse of cot theta equal to theta if theta belongs to 0 to pi. See, the proof of these results is derived as in the case of the sin theta, sin inverse of sin theta equal to theta. Using these ideas, we can derive these results also. These 6 results comes under property 1. Okay? Second property, this property also consisting of 6 results is under property 2. The first result is sin of sin inverse x is x. The first property we will see sin inverse of sin theta. First property we will see sin inverse of sin theta equal to theta. This is your property 1. Like that, sin inverse of sin theta equal to theta. This property, like that 6 results you have seen. Similarly, the second property, the first result is sin of sin inverse x. Here sin inverse of sin theta. Here sin of sin inverse x is equal to x. If x belongs to the domain closed interval minus 1 comma 1. The domain of sin inverse x is minus 1 comma 1 closed interval. Proof for this is you will consider sin inverse x by theta. You consider the sin inverse x by theta from this operating sin on both sides, x equal to sin theta. Okay. Sin inverse x equal to theta implies x is sin theta. And you replace theta by sin inverse x now. So x equal to sin of sin inverse x. Theta is replaced by sin inverse x. Therefore x equal to sin of sin inverse x. That's all about the result of this. Proof of the first is sin of sin inverse x is x. Considering sin inverse x equal to theta, x is sin theta, and replace theta, you will get x is sin of sin inverse x. Sin of sin inverse x. Similarly, other results we have seen. Second result is cos of cos inverse of x is equal to x, where x belongs to the domain minus 1 comma 1 closed interval. Third one is tan of tan inverse x is equal to x if x is on the real line. Fourth one, cosecant of cosecant inverse x is x if x belongs to the real line except the open interval minus 1 comma 1. The real line except that interval minus 1 comma 1 is the domain of cosecant inverse x. Fifth one, secant of secant inverse x equal to x if x belongs to the domain real line except the open interval minus 1 comma 1. The same domain for cosecant and secant inverse. Finally, sixth one, cot of cot inverse x equal to x if x belongs to the real line R. So these are the 6 results under property 2. Okay. Now property 3. That property 3 is also called reciprocal inverse identities. The property 3 is called reciprocal inverse identities. The first result is sin inverse of 1 by x equal to cosecant x. If x belongs to the domain real line except minus open interval minus 1 comma 1. Proof for this first result is consider sin inverse of 1 by xi by theta. Consider sin inverse of 1 by x by theta. From this 1 by x equal to sin theta. By the property of inverse, sin inverse of 1 by x equal to theta implies 1 by x equal to sin theta. And taking reciprocal on both sides, 1 by x becomes x. The sin theta is 1 cosecant theta. Taking reciprocal on both sides, x 1 by x is x, 1 by sin theta is cosecant theta. So 1 by x is sin theta, x is cosecant theta. Okay, taking reciprocal. From this, theta equal to cosecant inverse x. And you replace theta by sin inverse 1 by x. So cosecant inverse x equal to sin inverse 1 by x. Sin inverse 1 by x equal to cosecant inverse x, sorry. Sin inverse 1 by x equal to cosecant x. Cosecant inverse, sorry. The result is sin inverse 1 by x is cosecant inverse 1 by x. So x. Similarly, secant inverse 1 by x, cos inverse 1 by x is secant inverse x. Tan inverse 1 by x is this. Okay, small correction. Sin inverse 1 by x is equal to cosecant inverse x. To prove this, if x belongs to the domain real line except open interval minus 1 comma 1. So consider sin inverse 1 by x by theta. Therefore, 1 by x equal to sin theta. Therefore, taking reciprocal on both sides, you get x equal to cosecant theta. From this, theta equal to cosecant inverse x. And you again replace theta by sin inverse 1 by x. Therefore, sin inverse 1 by x is cosecant inverse x. That's all about the proof of the first result. Okay. Similarly, second result, cos inverse 1 by x is secant inverse x. If x belongs to the real line except to open interval minus 1 comma 1. And third one is tan inverse of 1 by x equal to cot inverse x. X is positive, minus pi plus cot inverse x if x is negative. These two results is also proved by the same method of the first result. Okay. Next, property 4 called reflection identities. The first property 4 in the first result, reflection identities. First result is sin inverse of minus x equal to minus sin inverse of x. If x belongs to the domain closed interval minus 1 comma 1. Sin inverse of minus x equal to minus sin inverse of x. If x belongs to the interval minus 1 comma 1. Proof. Let us consider sin inverse of minus x by theta. So from this, minus x, sin inverse of minus x equal to theta implies minus x equal to sin theta. By the property minus x equal to sin theta. So multiplying both sides by minus, I get x equal to minus sin theta. You know minus sin theta is sin of minus theta. We know that sin of minus theta is minus sin theta. Therefore, I can write this minus sin theta by sin of minus theta. Left hand side we have x. Again, by operating sin, you get sin inverse of x. The sin inverse of x equal to minus theta. So sin of minus theta is x. From this expression, I get minus theta equal to sin inverse of x. But minus, again, multiplying both sides by minus, you get minus sin inverse of x equal to theta. Minus sin inverse of x equal to theta. What is theta? Sin of minus, sin inverse of minus x. So replace by theta is sin inverse of minus x equal to minus sin inverse x. So sin inverse of minus x equal to minus sin inverse x is proved. By considering sin inverse of minus x by theta, it becomes minus x equal to sin theta. From this x equal to minus sin theta, multiplying both sides by minus. But you know, minus sin theta is sin of minus theta. Again you get minus theta equal to sin inverse of x. Again multiplying by minus on both sides, you get minus sin inverse of x equal to theta minus of minus plus theta, and theta is sin inverse of minus x equal to minus sin inverse x. Result proved. Similarly, other results. tan inverse of minus x is minus tan inverse of x if x belongs to the real line. And third one is cosecant inverse of minus x equal to minus cosecant inverse of x if x belongs to the domain real line except the open interval minus 1, 1. Fourth one is cos inverse of minus x is pi minus cos inverse of x, where x is belongs to the closed interval minus 1, 1. Similarly, secant inverse of minus x is pi minus secant inverse of x, where x belongs to the domain R except to the open interval minus 1, 1. Finally, cot inverse of minus x equal to pi minus cot inverse of x, where x belongs to the real line R. These six results comes under reflection identities. That's all about the property 4. Now I am going to stop my video here and we will continue the remaining properties in the next video. Thank you.